All right, hear me out. 1 second. And this table is wobbly as fuck. That might become an issue. I thought I was done for this year, but I thought about um, day 21 a bit more in my off time. And Jesus Christ, this chair is very bad. This table, I mean. I think if I put my foot on it, it should be fine. And I think I might have an idea that I want to try. Um, it might not work, but it might. We'll see. Just pounding back the Celsius. Not sponsored. Okay. So my idea is that if I define a method that's called minimum amount of steps between two letters with um this many layers left, then if you call that method with 0 layers, it returns um 1, I guess, or whatever. And if you call it with 1 layer, then it tries all the possible movements and calls the next layer recursively. And if we memorize this method, then we're going to be able to make use of the repeating patterns. And every combination of 2 letters, which is only 25 letters, is only ever going to get called once. And then we memorize that times 25. So 25 times 25 times 25 is 15,000. That's not too bad. That fits in a memoized cache. So I think that's what it is. I think that's the answer. I just quickly need to clean out my workspace here. Let's see. And once again, I'm just going to mute my music because I'm going to listen to copyrighted music. Okay. Let's see, shall we? I just realized I didn't stop tracking my hours yesterday. That's just great. Uh, maybe? Yeah, that should be fine. All right. All right. So let's start sharing my screen. And let's start opening Atmos code. And then I want to start popping out my chat. Well, Merry Christmas first and foremost. I haven't really said that yet. It is the 25th. And I only have about 30 minutes right now. I might come back to this later today. And by 30 minutes, I think I mean 50 minutes or so. Okay. So here's what I'm thinking, all right? How do you do memoization in Python again? Memoization. I think it's called um, add memoize. Well, he implemented it from scratch. Yeah, that's well. Add functools cache, which I think I already have installed in my template. I do not. Great. Okay. So here is my thinking. So we define minimum amount for levels. And then we have a from key and a to key, and then use keypad a equals false. And then levels. Let's start at 0, I think. No, that doesn't really make sense. I don't think we should have a default value there. So how did we do fast sequence again? Fast sequence we did. Where's, oh, there it is. For S in stride, we do movement plus A. So we attach A before stride. Let's just copy this. And then we don't want movement, we want all movement, I guess. Okay. From key to key. Or do we give it a whole line? Let's try giving it a whole line, shall we? And then levels is just the amount of levels we want to add. So if levels equals 0, return len of line. Okay, but this doesn't work because we don't want len of line. We instead want the format of having a dictionary which contains sequences and amounts for those sequences. Right? So we have a dictionary of sorts. Yeah, we might as well do this. And then this we do return the sum of k times v for kv in items. And we never turn it into an array, I don't think. Okay. Lookup result for in sequence dict items. for m in this, m plus equals uppercase A. I think that's right. And let's call it choose stride to just make it a little easier to understand. So we're trying to what are we trying to? Okay. I need to fix this goddamn table. I'll be right back. I'm gonna get some like paper towel. Okay. So there is a semblance of an idea here. Did I fix it? I think I fixed it. I mean, it's not perfect, but it's much better than it was. Okay. So I don't think this is right. I don't think we ever want to turn anything into dictionaries again. I think we do have a line. Um, and then I think what we do is for I never called Ash. If levels equals 0, return the length. For S in toStride A plus S. For M in movement. A if else B. Maybe. Maybe this is just it, but I don't think it is. I really don't think it is. I think it's 3. I mean, look, let's just run it, see what happens. Why is T0 a list? T0 is not a list. What? T0 should be a string. Oh, very interesting. Huh. I don't think I want that. And I think I should be able to very easily just change this up. S underscore is not defined. Key error 3. I see what you were saying. Okay. Well, that did something. So this is supposed to return 379A. 64. All right. Um, or line in T, print this. Got the wrong test string. 68, 60, 68, 64, 64. You got it. Okay. So now we do 25. This is the moment of truth. Okay, seems to have worked. S equals 0, S plus equals this times end of line, replace A with nothing. Print S, and then the same for 25. God damn it. I don't believe you. This has to be the right fucking answer. It just has to be. Why are you doing this to me? I don't get it. I don't get it. Wait, am I using all movement or am I using movement? Because if I'm just using movement, then that explains. I am using movement. No, wrong method. I am using movement. I think that's it. I think we got it. Okay. Now we got 3 minutes and 52 seconds to clean up our code. So this is toast. 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 Never needed that one. Or these for that matter. Don't need that one. Put you at the top. I don't think I need get IDX. Maybe I do. Let's see. Don't need seeded sort. All movement. I don't think I need movement because I already have all movement. Am I ever using inverse IDX? I don't think I. I'm definitely using these. Yeah, that's it. 100 lines of code. So this easy the entire time. I think we could definitely clean up this method a little bit, but that's fine. Man, once again, it was memoization. If I got this right, then memoization is like a coder's dynamic programming, right? Like it's dynamic programming, but you don't have to think about the dynamic programming. Because you don't make a table of values that you reindex, you just store. Is that right? I think that's right. I don't know. Maybe I'm making this up. But I have a feeling that I previously solved a dynamic programming problem with add cache. Wow. Wowie zowie. Um, let's see if there's more difficult problems here. Doesn't look like it. Okay. So that was 21. Let's take a look at 22. The random numbers. Okay, I don't think I'll be doing day 24 today because that one looked pretty tricky. Um, hmm, 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 hmm. Let's just read the whole thing. I mean, we got time, right? This is going to be another, oh, 30 seconds. Maybe we don't have time. Run levels. Levels plus one. And then we do run of 2 and run of 25. Okay. Yes. Finally. Jesus Christ. At day 21. Wow, that sucked. That sucked big time. And what sucks even more is that it was this simple. Um, ugh. Whatever, man. Don't dwell on it. Let's just move on. I think, yeah, this is how we get to the next one. You're all teleported deep into the jungle. The monkey stole device. Sure, monkey market. Market is full of monkeys buying good hiding spots. Fortunately, because of the time you recently spent in the jungle, you know lots of good hiding spots. If you sell enough hiding spots, you should be able to get bananas. Buyers seem to use random prices, but their prices are actually only pseudo-random. If you know the secret of how they pick their prices, you can wait for the perfect time to sell. The part about their secrets is literal. The part about secrets is literal. Each buyer produces a pseudo-random sequence of secret numbers where each secret is derived from the previous. Multiplying by 64. To mix a value, calculate the bitwise OR of the given value and the secret number. Calculate the result of multiplying the secret number by 64. Then mix this result into the secret number. Finally, prune the secret number. See, the question is, like when you say secret number, do you mean the evolved secret number or the one from the previous step? Mm-hmm. All right. So we do, well, first of all, we need to do this. Um, so we iterate n equals n times 64 and n. Mod this number. Divide by 32, mix into secret number, prune. Divide by 32, multiplying by 2048. Wait, do I not have don't disturb turn on? 2048. All right, so let's print iterate of 1, 2, 3. Let's see what happens. None. Well, maybe we should return n. How about that? 0. Huh. Why is that? 15. Wait, what? 24 is 10. Oh, it's X or not and. Stupid. Okay, you got it. I think that's the right number. Yeah, okay. Each buyer uses their own secret number. This list describes initial secrets of 4 different monkeys. In a single day, buyers each have time to generate 2,000 new secret numbers. This example, for each buyer, their initial secret number in the 2000s would be this. I see. So s equals 0 for n in G, s equals this. Return, no, print s. Um, if k greater than 1, return iterate n minus 1. Okay, so you got it. Maximum recursion depth 3. That kind of makes sense. For underscore in range k. And it's not 1,000, it's 2,000. Ding, ding, ding. What's part 2, though? The buyer offers are just the 1th digit? Oh, so yeah, mod 10. You still don't speak monkey. The monkey only shows how to decide when to sell by looking at the changes in price. Uh-huh. Look for a specific sequence of 4 consecutive changes, then immediately sell when it sees that sequence. So if a buyer starts with a secret number of 1 to 3, the first 10 secret numbers, prices, and rate changes would be these. Where? Minus 1, minus 1, 0, 2, minus 2, 0, minus 2. Within just these first few prices, the highest price will be 6. It would be nice to give the monkey instructions that would make it sell at that time. The first 6 occurs after 2 changes. There's no way to instruct the monkey to sell then, but the second 6 occurs after minus 1, minus 102. So if you give the monkey that sequence, it will wait until the first time it sees that sequence. Each buyer wants to buy one hiding spot. So after the hiding spot is sold, we'll move on to the next buyer. If the monkey never hears that sequence, the monkey will never sell. You can only give the monkey a single sequence of 4 price changes to look for. You can't change the sequence between buyers. You're going to need as many bananas as possible, so you'll need to determine which sequence of 4 price changes will cause the monkey to get you the most bananas overall. Each buyer is going to generate 2,000 secret numbers. Uh-huh. Okay. Interesting. Interesting. Oh, very interesting. Very, very interesting. I see. So we find sequence, n sequence. V is hist is a list, or 0, actually like minus 99 for underscore in sequence. For I in range 2000, and new is iterate. Let's just set it to 1. Diff equals nu minus n is nu. Hist.append diff and hist remove first value. If tuple of hist equal to sequence, then we return n, I believe. Return 0. So now we should be able to find, let's say this is the sequence. Okay, so let's print find sequence to this tuple 0. Well, that's not great. I'm an idiot. Diff is mod 10 minus n. Mod 10. That's more like it, I think. Yeah. 7. That's right. Okay. I'm just going to print some diffs to see what the ranges are here. I mean, it should go from +9 to -9. No? Yeah, there we go. All right. So for a in range of 19, a minus equals 9. So then this way it goes from 18 up to 18, which minus 9 is 9. Okay. And then we do this 4 times, except each time we give this one a new value. E. This will most definitely have a horrible, horrible runtime. 20 to the power of 4 is 160K. So we need to do this 160K times. And running 1 already took like a second. So this will not work. So we definitely need to remove the print. Oh, we can close you. And then I would say we print C. Okay, so C goes pretty fast. Let's take a look at A. A does not go pretty fast. It is moving, shockingly enough. I think we could most definitely get to the bottom of this. Um, well, we still need to do this for every line in T. Yeah, I see. So now it's no longer feasible. Um, huh. Okay. So we got actually it's 19 to the power of 4. That's 130K. Now, what's 130K times this number? That's too large of a number. So we can speed up this process by doing a lookup table that's 16 million entries long and just going to the next one in that lookup table. So, I mean, it's the same thing as if I were to put a cache here. Uh, at cache. I don't know how much faster it's going to get, to be frank. Not much faster. Not much faster at all. So for every sequence of numbers, we can go through do they loop? Probably not. So there really are 16 million of these. So let's see. Um, so if we define a cache, right? And then the problem is we have to go backwards. That's the problem. Like we can't just we can't fill the cache as we go. We have to sort of go backwards. Um, I mean, that's fine. We can just keep an array of 1,000 numbers, 2,000 numbers. That's not a big problem. Um, so what we would do is, wait, do I have to go? I think I have to go. Okay, I can solve this. I think I have an idea of how to solve this. Maybe I'm not leaving, at least not immediately. So I think we got some more time to figure this one out. So basically, what I want to do is store a numbers array. And then we do numbers append nu. Okay, so we add a cache. If n in cache, then we return cache found and I cache. So we do, so the cache is going to be filled with return, or the result in the distance is cache. If I plus dist is greater than 2000, we would return 0. Otherwise, we return result. Now, this might be an off by 1 error. We'll figure this one out in a second. And then here, we fill cache with numbers, I, and cache. And numbers has already been appended by the number. So for n in numbers -1, the distance starts off at 0, and then the distance plus equals 1. Why do we need I? I don't think we need I. So we need the result, I think, is what we need. Result. Right? So for every number, we store that we found the value and what the distance is. Yeah, that sounds about right. Still incredibly slow, just very, very slow. Why is it so slow? I don't know. I do not know. I think I wanted to charge my AirPods case. I haven't done that yet. That's a little unfortunate. But I will live. And also, I think, wanted to charge my phone, but I also haven't done that either. Okay. So I am a little stumped here. Ah, I think I know what to do. I think we need an add distance value, which starts at 0. We plus equal 1. No, uh, this one gets the distance added. And then we fill cache with 0 and 2001. Okay, I think that's much better. So if we don't find the number, we know that none of these numbers will ever find anything. It's not really getting much faster, unfortunately. It's not really getting much faster. Okay. I think it might be time to think about this off by 1 error here. Um, yeah, I think this is right. I think this is right. So I think the logic here is sound, but it's not very well optimized at all. And I don't immediately have an idea of what to do about that. So the sequence is unique every time. The sequence is unique every time. You know what? I think this part is very, very stupid. Because we can only have wait, is it even 4 numbers? Yeah. So we need to take a look at um need to take a look at 5 numbers. Um and then the sequence is, so let's get rid of all these. It's gonna be I think it's B minus A, C minus B, B minus C, and E minus D, right? So it is getting faster now, to the point where we still definitely cannot run this. So that's very unfortunate. I mean, uh, what else could we be optimizing? I don't know. We could check. We're still caching iterate. So we can just pre-fill the numbers. So we would go about this all differently. Um, but the cache can't be filled by. So if we have 2,000 numbers in a row, how easy is it to find any given sequence in it? And is it much faster than doing what I'm doing here? Maybe, probably. So how about what happens if we remove this cache? Probably doesn't get much faster. No. What if we do um let's see. So we got diffs is an empty array. And then let's keep this one for now. Let's keep this one for now. I mean, this is fine, right? This doesn't take too long to run? No, it does not. Okay. For line int, no, for n in t, for underscore in range 2000, diffs append. This is almost correct, except we do n new, and we do n new minus n, and then n is n new. Is that right? I think that's right. And then we could even go one step further, and we say, um, for uh, diffsys. There we go. That's better. For diffs in diffsys, and then for I in range len of diffs minus 1 gives me length of 2, so -3 gives me a length of 4. And then we got diff dictionaries. And then the diff D is this. And the diffs B append this. And then we got a sequence. Wait, no, this is not right. It's this, I think, right? We got a modulo both numbers. I think I want to append maybe a tuple of the difference and the value. And then how about we do D for Dn in diffs I plus 4. Right? Right? Yeah, that's 4 numbers in a tuple. All right. And then diff D of sequence is diffs I plus 3, 1, perhaps. And that still resolves pretty quick. So now we find, okay, how do we test this? Well, we can just put in these test values. And then the number 1, for the buyer of number 1, these changes occur for value 7. So let's see if that works. So we print diffs D 0 for initial value 1. Oh wait, I have to leave like immediately. Okay, I'll try this thing and then I have to go. So we're trying to see if this sequence produces 7. And I think it should. 4. Okay. That's not great. But at least we found it here, I guess. It might be an I+4 angle. Um, but that's gonna cause like different kinds of issues. Um, hmm. The diffs leading up to it. I don't know, man. I feel like we have an off by 1 error here again. Like in the first 2000 numbers. Let's see. For D and diffs D, print D dot get 0. Okay. So we get 7, 7, nothing, 9. So it might just work. Might just work. You know what I think the issue is? I think we want to put n new and not n. There we go. Yeah, that's right. So we did have an off by 1 error. Okay, that's good to know. So, um, now we need to find what the optimal sequence, what's the most bananas you can get. So, the max V is 0. And then we do max V is max of n for n in T. And then actually let's do D for D in T. And then except T, we do this. And we do sum. We do D dot get diff 0. And then we print max V. Let's see. Int object is not iterable. What? Huh? Oh my gosh. Okay. It's max, max, V, and this. It does take a second. This code is not very optimal at all. Um, but I think we should get there in the end. Maybe, hopefully, fingers crossed. Let's see. Um, oh, there's a lot of printouts. Let's maybe remove those. And then how about we just print the outermost loop. Okay, so it is working. It's just taking a second. All right, that's good enough for me. Let's run this and see if it works. And then I have to go. Too high. Well, how's that possible? How's that possible? So what do we get for fringe? What do we get here? 23. Yeah, that's right. What is the most bananas I can get? I'm a little confused by how it's possible that I got a too high value. That is very strange. That is very, very strange. I'm not sure. I'm not sure. Doesn't really make much sense to me, to be quite honest. We can definitely make this a little faster by only taking a look at all the sequences that are actually happening instead of, all the values. I don't know. I'll think about it. I have to go. I might be back for a bit later. But I'm very, very happy that we got 21 done. Oh my gosh, 21 was a huge, huge pain in the ass. That was so difficult. All right. Merry Christmas. I'll be back. Bye-bye.